We want to predict the probability of machine failure based on the current operating conditions. It has a profound business applications. We basically want to capture the problem before things blow up. In this case, we deal with binary classification problem, so the response variable is machine failure, coded as 0 versus 1. 1 stands for failure. And we have 4 available predictors. We have 2 different measures of temperature. We have a measure of rotation speed and measure of the torque applied to the blades or the internal mechanism or whatever it is that we're dealing with. So in this case, the data set is presented here. This is a short snippet. We are trying to predict machine failure. That's our response by looking at 4 available predictors represented here. And to make this problem more visual, so to say, here's an example of what that failure might look like. So if you imagine a wind turbine, when things go wrong, that catastrophic failure really does result to things blowing up. So you can think about those 4 variables as rotation speed of the turbine, the torque applied, and 2 different sensors to temperature. Let's say the temperature within that casing of the turbine, and let's say the temperature of the coolant in the cooling system, or something like that, okay? So let me show you how easy it is to run TreeNet here. All you need to do is go under Predictive Analytics module, pick TreeNet for classification, fit model. In this case, we're dealing with binary response. That's the machine failure. We pick 4 continuous predictors. Then we set up certain validation parameters, validation of the test set at 30%, and set a bunch of options, like we will do 300 learning cycles with a learning rate. In this case, I will lower it to 0.05, and we will be seeking for the optimal model based on the area under ROC curve. So once I get the final output, I can look at different results and evaluate what kind of model I have. So let's have a detailed look. And again, this is a reminder of the importance of the problem that we are trying to solve here, because the machine failure could be a very spectacular and dramatic looking event. So in this case, TreeNet learning process shows what happens to our test sample performance in terms of area under ROC curve as we keep adding more and more incremental learning cycles. Because remember, this is the boosting process. We're learning incrementally by trying to correct errors of all of the prior learning stages. Now notice that on the training set, the blue curve, we can potentially learn all the way to perfection, but it is the test set that is of most interest to us, because the test set reveals the true amount of learning. And in this case, the optimal model has about 60 different trees or 60 different learning cycles. The model also reports variable importance according to their contributions. And if you look at the model summary in this case, you will discover that our performance on the test sample is very close to 90% area under ROC curve. It is instructive at this stage to recall from previous webinar what were the accuracies achieved by single cart, and that was actually at 0.84, and by a random forest model, and that one was actually 0.89. TreeNet in this case manages to beat even random forest by a little amount, but still sizable. And that's again yet another great confirmation on the general level and degree of learning that we can achieve with some of these modern powerful machine learning techniques, TreeNet being one prime example of such. Now, at this point, we know that we have a good performing model, but the real advantage of TreeNet is that in addition to capturing your response with a very good accuracy, it also allows you to interpret what the model is actually doing. And that's going to be my next slide here. This facility is called as TreeNet partial dependence plots. So for every variable that is part of the final model, TreeNet can construct the nature of dependency as attributed to that variable once everything else is being averaged out. So the first such variable is going to be the torque. And in this case, we can identify by the nature of this dependency, the graph itself shows the contribution of different levels of torque towards the failure of the machine. So we can observe from here that there is two areas. One area is the area of the low torque. That's when the odds of machine failing increase dramatically. The other area is the area of high torque. This is the area where, again, the odds of machine failure begin to increase dramatically. This is a great example of what we call a nonlinear relationship because it actually shows the reversal of the trend when you go to one or the other extreme. Similarly, if you look at the rotation speed, the graph exhibits a very similar switching behavior. When the rotation speed drops below 1400 RPM, there's a significant increase in the odds of failing. Likewise, when the rotation speed exceeds above 2500 RPMs, we have a similar dramatic increase in the odds of failure. Now, as far as the remaining variables, there's this air temperature sensor, and from here it becomes clear that when that air temperature sensor increases above something like 301 Fahrenheit, there is an associated high possibility of machine failure. You can think about it as the sensor that is right there under the casing of that power module of the turbine. So when that turbine is starting to overheat, the air temperature shoots above 300 something degrees, and that's where you have a high odds of failure occurring. And the fourth variable here is the process temperature. You can think about it as a coolant temperature, and when the cooling system is not functioning properly, that coolant system temperature can drop because it's not being circulating into the main area, and then again that could be associated with increased odds of failure. Now also I want you to pay attention to the vertical scale of these graphs. Even though they look the same, the actual amplitude will be very different as you go from graph to graph. And in this case, the torque and the rotation speed are associated with the highest degrees of change. Now, TreeNet can also produce bivariate plots, not just univariate plots, and those are instructive. When you look at the bivariate plot between torque and the rotation speed, you can actually see that what we have here is an interaction between those two variables. You can also see it by looking at the heat map, where we use different color to show different values of the z-axis in this case. Well, it becomes very clear from this plot that the areas of danger are the areas when you have low torque and high rotation speed. That basically means that the turbine is spinning out of control, and the centrifugal forces can produce the associated failure of that machine, right? Or just some natural friction within the shaft. On the other hand, another area of danger would be the area that has a high torque and low rotation speed, which means that the grid overloads the turbine, and it's becoming progressively harder and harder to rotate it and to move the blades, and ultimately that can create internal rise in temperature and all these other things. So notice, because of the presence of this interaction, when we were to look at torque and rotation speed individually as univariate graphs on the left, we could actually see those nonlinear tail rises, but the reality is that they are the result of this interaction, which is a lot more prominent when you look at that TreeNet plot in a 3D scenario. So that gives us tremendous amount of learning. Now, you can rewatch prior webinar and look at CART insights, look at random forest. Well, random forest, there was no insight, so it's just good performing model. In the case of CART, we did obtain different segments, and you can actually see by comparing how those CART segments roughly communicate a lot more detailed picture that we can now obtain here by running TreeNet. And that's why I love this algorithm, because it allows you to see a lot more detail of what's going on, including at the level of interactions. But let me move on to our conclusion here. The conclusion is that TreeNet allowed us to identify nonlinear regions of machine operation that may lead to a catastrophic failure. And the TreeNet achieved so far the highest performance of 0.9 in terms of area under ROC curve. And the TreeNet model generates, therefore, powerful insights into the nature of dependencies by supplying 2D and 3D partial dependence plots. And that's basically what we have with this example.